welcome to Chapter 6.1. We are going to start talking about chemical bonds and chemical reactions. And we're going to start off by reviewing or taking a look at ionic bonding. So, how do atoms form compounds? It's actually not that complicated. It all comes down to electrons. So you may remember that we talked about reactivity as being a property of elements. And reactivity depends on the number of valence electrons there are in the atom. And if you remember, valence electrons are the electrons in the outermost energy level. So if you look at this picture here, the blue dots would represent the valence electrons. So this has 2 valence electrons. And it turns out that all atoms want to become stable, meaning they want their outer shell to be filled with electrons. But this only happens when they have the correct number of electrons. And it turns out that magic number is 8. So if we take a look at the noble gases over here, neon, argon, krypton, xenon, all of these are very unreactive elements. They very, very rarely form compounds with other atoms, meaning they very rarely form bonds with other atoms. And that's because they have 8 valence electrons in their atoms. They have 8 electrons in their outer shells. Now, helium, it turns out, also fits into this category, even though it only has 2, but that's because of the structure of the atom. So if you remember, we talked about the Bohr model, and the Bohr model has a nucleus, and then it has some energy levels. The first energy level only holds 2 electrons, and then the next one holds 8. That's what we're talking about here. For helium to have a full outer energy level, it only needs 2 electrons. Everything else requires 8. And now, in order to easily see which atoms are stable and which ones want to become stable, we use something called an electron dot structure. And an electron dot structure is when you take the elemental symbol and you put 1 dot for each valence electron it has. So, when we talked about the periodic table, we talked about the fact that all of the elements in a group or family together have similar properties because they have the same number of valence electrons. Hydrogen is placed over here with all these metals, for example, because, like lithium and sodium and potassium, it only has 1 valence electron. So the first column in the periodic table, column 1, group 1, are all the elements that have 1 valence electron. The next one over are all the elements that have 2. Skipping the transition metals, way over to group 13, these are the ones that have 3 valence electrons. 4, 5, 6. The halogens have 7, and the noble gases have 8. And we can represent all of those by using this electron dot structure format. Now, learning how to do these electron dot structures is going to be very important because we're going to actually combine multiple dot structures together to figure out ionic bonds. So atoms react in order to become stable. They react in order to get a full valence shell of electrons, a full 8. Some elements achieve this by actually giving away or getting electrons from other atoms. So transferring electrons from one atom to another. And this is what's called an ionic bond. So here you can see sodium. And our little sodium atom only has 1 electron. And we know from our chart, / the periodic table, sodium only has 1 electron. And chlorine is way over in the halogen group, in group 17, which means that it has 7 valence electrons. So chlorine would be awfully happy just to get 1 more electron. And sodium, it turns out, would be really happy to get rid of that electron, because once it gets rid of it, the next energy level down is going to be the highest energy level, which is already full of electrons, and thus once it gets rid of that electron, it has a full valence shell. It's just the next level down. Now, when that happens, when this electron gets transferred from sodium over to chlorine, chlorine is gaining a negative. So it goes from a neutral atom to a negatively charged atom. And any negatively charged atom is called an anion. It has a negative charge. Now, sodium gave away that negative charge, which means it now has extra positives. It's not balanced anymore. So sodium is now positively charged, which makes it what we call a cation. And these, whether it's a cation or an anion, are called ions. An ion is a charged atom. A positively charged atom is a cation, and a negatively charged atom is an anion. And now the whole reason why sodium and chlorine are going to attract to each other and bond to make sodium chloride, which is just simple table salt, are because when it comes to electric charges, opposites attract. This positive is now attracted to this negative so much that they actually form a little bond between them. And that only happened because the electrons were transferred from one atom to another. This is what we call an ionic bond. It's a bond that forms when a cation and an anion attract and hold each other together. And this is what we call a chemical bond. A chemical bond is any kind of bond that holds atoms together. We're going to learn about 3 different kinds, but right now we're talking about an ionic bond in particular. So remember that atoms become cations and anions in order to get a stable electron configuration. That's the whole reason they're doing this. How easy it is to do this is called the ionization energy. So for example, all of these halogens right here, they have 7 valence electrons. They want 8. So it's really, really easy for them to gain 1 to get to a full valence shell. And it's so much easier to do that than to lose all 7 to get to a full valence shell. So we call this having a high ionization energy. It would rather get electrons than give them away. It's really, really hard to remove the electrons over here. However, on the other end of the table, the alkali metals over here, they only have 1 electron. And they are trying to get rid of that thing because once they get rid of it, the energy level below that one will be full and it'll be satisfied. It's really, really easy to take this electron away to satisfy that full valence shell. A lot easier than it would be to add 7 more electrons to get way over here. So we say that these have a low ionization energy. It's very easy to remove the electrons. And as you can see from the trends on this table, the ionization energy increases as you move across the table, meaning it gets harder to remove electrons as you move across the table. And it also increases from bottom to top. So the general trend is from the bottom left corner to the top right corner. So francium is incredibly reactive. It has that 1 electron and it's super, super easy to take that electron from it. So francium will bond with almost anything. And when that happens, it releases a ton of energy. Francium is really, really, really explosive in water. Now over here, these are harder to remove the electrons. That doesn't mean that these are less reactive. It turns out that the halogens are also really reactive because they only need a difference of 1 electron. They only have to gain 1 electron to become, have a noble gas configuration, have a full valence shell. So it turns out that fluorine is actually very, very reactive because it's really hard to remove their electrons, but it's easy for it to gain them. This is why you're not supposed to swallow toothpaste or mouthwash that has fluoride in it, because over time the fluoride can actually build up in your body and it's so reactive that it reacts with other compounds in your body and it can cause a lot of damage. Now, compounds that contain ionic bonds are what we call ionic compounds, and these only happen between metals and nonmetals. So we could not form an ionic bond between lead and potassium because both of those are metals. We also couldn't form an ionic bond between carbon and oxygen because both of those are nonmetals. But we can form an ionic bond between iron and oxygen because iron is a metal and oxygen is a nonmetal. Metals want to give away their electrons in general to become cations or positively charged, and nonmetals want to take those electrons to become anions, or negatively charged. And that's where we get those opposite charges that end up attracting. Now, we can represent an ionic bond by something called a chemical formula. And a chemical formula is a notation that shows what elements are in that compound and what the ratio of those compounds are. So, for example, if we think back to our original example back here, we can think about sodium chloride, or table salt. Sodium chloride has sodium, which is symbol Na, and it has chloride, which is symbol Cl. And it's actually written out NaCl. And the reason why it's written like this is because the cation comes first, and then the anion comes after. And there's one sodium atom for every one chlorine atom. If this were NaCl2, that would mean that we have one sodium atom for every two chlorine atoms. So there would be two of these guys. But that's not the case here. With sodium chloride, it's just one sodium atom and one chlorine atom. So let's take a look at how an ionic bond forms. For example, let's look at magnesium and chlorine. The first thing we want to look at when we're given a problem like this is we want to figure out how many valence electrons each of these has. So if we look at magnesium on the periodic table, or over in this little cheat sheet, we can see that magnesium has 2 valence electrons. So if I'm making my electron dot structure, I put 2 dots. Chlorine has 7. So I have to draw 1, 2, 3, 4, 5, 6, 7. Now, you could see it would be a lot easier for magnesium to give up these 2 electrons to go somewhere else, and it'd be easier for chlorine to gain an electron than it would for chlorine to try and get rid of all 7 of these guys, and magnesium to collect a whole 6 electrons to get to a total of 8. So what is going to happen is this magnesium is going to give up one of its electrons, and it's going to go over to chlorine. And now chlorine is totally happy right now. It has a full valence shell. But magnesium isn't happy yet. You can see magnesium still has 1 electron left in its valence shell. This indicates that one magnesium atom does not bind with just one chlorine atom. It turns out that magnesium atom has to bind with another chlorine that also has 7 valence electrons. And then this leftover valence electron here gets transferred over to this chlorine atom to make it totally happy. Magnesium, though it looks pretty lonely, it doesn't have 8 electrons. It does have a full valence shell because it got rid of all of the electrons in that outer shell, so that now what's considered the valence shell is the next level down, and that is full. So now we have one magnesium atom that's totally happy, and it is positively charged because it gave up its electrons. And we have 2 chlorine atoms, and these are negatively charged because they gained those electrons. And because these are negatively charged and these are positively charged, they're going to come together and they're going to make a chemical compound that we can represent with a chemical formula. So remember, our chemical formula has the symbol for the elements that we're using and how many we have. So we have 1 magnesium atom for every 2 chlorine atoms. So this is MgCl2. So that's how an ionic bond works. Now, because of the way that these electric forces work between the positive and negatively charged ions, ionic bonds tend to form in really organized ways. We get things like salts and crystals when they form, because they form this really, really tight lattice structure. A lattice structure means that the type of atom alternates in every direction, all the way around. So you can see from this crystal that this is very, very structured. And it turns out that the properties of an ionic compound can be explained by these strong attractions within this crystal. Ionic compounds tend to have a really high melting point, and they tend to be really good conductors of electricity when they're dissolved in water. The high melting point is due to the tight attractions between all of these atoms. You have to pump in a lot of heat energy in order to break those bonds apart so that these atoms can move around each other. The conducting electricity when dissolved in water has to do with their charges. If you dissolve a compound in water and it releases positive and negative charges, those charges will help conduct that electricity. So that's ionic bonds, and here are your homework questions.